Okay, just getting ready to go live, everybody. 5 minutes because Twitter needs to play catch up all the time. Just do a quick sound check. Okay, just getting ready to go live, everybody. Minutes and we'll be ready to rock. Right, let's see if X is ready to stream. X has gotten a little better recently, actually. They tend to start up quite quickly now. Kind of surprised that they're, improving it, which is good, but still a surprise. Yeah, all right. X is up. We'll start in a second. Right. Here's where we were last time. Let me get the window share up. So we're back onto data structures and algorithms, and where we left off last time was that we just got to sorting algorithms, and we're just about to do bubble sort, which I've not done before. So this will be fun. And I stopped here last time because I was like, no way am I going to have like the brain power to get through this after I've already been through like 3 chapters of this. So let's have a little look at this now. So bubble sort. Wait, if the standard sorted function exists, why would we learn to write a sorting algorithm from scratch? We choose to write sorting algorithms from scratch, not because it is easy, but because it is hard. John F. Kennedy. In all seriousness, in this chapter we'll be building some of the most famous sorting algorithms from scratch because it's good to understand how they work under the hood. It's great algorithmic thinking practice. It's fun, at least for me. Bubble sort is a very basic sorting algorithm named for the way elements bubble to the top of the list. So let's have a little listen to the video. It's only a minute.
Bubble sort is the sorting algorithm that everyone learns, but no one actually uses in the real world because it's so slow. We learn it because it's easy to understand, and once we appreciate how slow it is, the other sorting algorithms are just that much more impressive. It all starts with an unsorted list of numbers. Then we loop from left to right and compare each pair of neighboring numbers. If the number on the right is smaller than the number on the left, we just swap them. Otherwise, we just leave them be. When we get to the end, we just go back to the start and do it again. We repeat this process over and over and over until we go all the way from left to right without making any swaps. Here's what it looks like on a larger data set.
Good video. Bubble sort repeatedly steps through a slice and compares adjacent elements, swapping them if they are out of order. It continues to loop over the slice until the whole list is completely sorted. Here's the pseudocode. So set swapping to true. Set n to the length of the input list. While swapping is true, set swapping to false. For I from the second element to the end, if the I minus 1 nth element in the input list is greater than the ith element, swap I minus 1th element and the I element, set swapping to true, decrement end by 1, return the sorted list. So assignment. While our avocado toast influencers were happy with our search functionality, they now want to be able to sort all their followers by follower count. Bubble sort is a straightforward sorting algorithm that we can implement quickly, so let's do that. Complete bubble sort function according to the described above algorithm. Okay, so we're going to have swapping is equal to true. End to the length of the input list, so end is equal to nums. Let's forget with Python, it's like that. Set end to the length of the input list while swapping is true, so while swapping is equal to true. Set swapping, so then we set swapping to false. Swapping to false. For num in nums, from the second element to the end. So we can't start from the first one for I. For I, from the second element to the end. Num in. We have to do it as a range, I think. We have to do that. So range. Iterating. Use positive step values, negative step values go backwards. How do you skip from like? How do you start part way through into it? Oh right, sorry, it's the first part. So range. Iterating from 2 to right. Okay. In a range, I'm not used to using this range function. So nums. In fact, I'll just do that for now and then just see what it prints out. So print num. See what it does. Right. I'm not sure how misleading that sort of like second part is and stuff, for like second element. So I'll just ignore that for now. We'll see if it comes back to it. So if I minus 1 nth element of the input list is greater than the ith element, swap I minus 1 the element with the set swap into true. So I guess if nums, suppose I need the like I don't so hold on, let me do this again. I do need this of like the it should count. So for what's the syntax again for the for? So we do 1 and then length. Hold on, we do end like that, and then we basically go if nums like that, I minus 1 is this is greater than nums I, then swap I nth element with, okay, so nums I minus 1 equals nums I. Put these in a variable to make it less like It's called minus 1 equals nums I minus 1. And I'll just put ith. Oh, one moment, most important job of the day. Hold on. One moment, folks. Righty ho. Job's done. Let's see where we're at. Right, still here. Good. Okay. Right. Wait. All right. Okay, just replacing these variables basically. All right. So height. That's going to be so we follow that logic, and then we set swapping to true. decrement n by 1. Oh, just by inside the if? No. So then end oops, minus equal 1. Return the sorted list. So then return nums. Let's see what that does. Probably a whole bunch of okay. So I'm guessing my problem is this, like you can't just like reference it like that, not like JavaScript, I guess. So can we do that? Can we do that? Do we have to make a fresh copy, or can we do nums? Can we just override what we were basically given? So not remembering all the Python just yet. Nope. Actually, so we didn't like sort any of it, so maybe we just have to have a new thing. So sorted underscore list. No, we can't do that. Hold on. Can we? No, yeah, it's not gonna like that. So guess if I did that. Sorted list. I bet some people are laughing and watching right now, but I'm going to still keep trying. Right, so I don't really make a difference. I'm getting mutability wrong with this, aren't I? Pretty sure. So I guess for this we do print nums and just see what it is as we sort of step through. Right, it never changes, so something's not right here. Does it ever hit this function? Print. Yeah, how do you come over? Right, control enter, so I have to keep doing that. Right, so it just hit but only once, which is strange. And just print this out. Print. Right, hold on. 5, so it should loop 5 times, right? So we do print I. Let's read this again. So if nth minus 1 element is swap the so swap these rounds equals What am I doing wrong here? So clone value or something. Reference versus value in Python. Hold on, yes, is the thing I'm missing. In Python, when you pass a value into a function, capacity by reference or value passed by reference, the function receives a reference to the original data. Changes made within the function affect the original data applies to multiple types of lists, dictionaries, and sets. Passed by value, the function receives a copy of the data. Changes made within the function do not affect the original data. This applies to mutable types as integers, floats, strings, booleans, and tuples. Pass by reference can lead to function impurity where a function unintentionally modifies data outside its scope. So pass by reference example. So shopping list, blah, blah. Okay, pass by example, pure function example. Learn functional program. Lists. Just look at indexing into lists. No, that's right, so I am doing that. Appending lists, list operation contains indexing, slicing lists in Python, reversing lists, updating list elements in. So look at that. Yes, that's essentially what I'm doing. Lists in Python, defining a list of weapons. It's just very basic stuff. List operation contains pending Python, mutability, functional programming. Slicing lists, reversing, updating list elements. So look at that. Sorting. Yeah, we don't want to use the sorted function, right? Let's look at it. Sorted. Closures in Python. Right, so do we need to make a copy of that list so we can just sort of fill it up? So if we did so if we had sorted list equals nums.copy. Can we do that? Then we do sorted list. And then we do we do sorted list I minus 1. Does that work? Nope, same result. It's going to be something really basic I'm doing wrong. I'm doing something basic wrong, but I can't figure what it is. But I feel like it's just a Python thing. I'm just screwing up. Let me just print what the sorted list is at that point. So when it hits, it's almost it did move it along. But that doesn't work yet because basically we swapped those two. We swapped 3 and 7, but it needs to swap them again. So it needs to go back round again. So do we only decrement so while swapping is true? So is that the key? I need to have the end outside of the thing. Maybe we don't need that. Did I miss a step? So set swapping to true. Set end to the length of the input list, so nums. Make a fresh list. While swapping is true, set swapping to false. For I in range, so from 1 to the end. Hey peeps. Hope you're doing well. I'm just catching it as a variable just so it's a little less messy. So then if the I minus 1th element is greater than the ith element, then swap I minus 1th element of the import list is greater than the ith element. Swap it, and then I don't need to do that part. Whoops, silly me. And then that can go back in the loop, I guess. Actually, no, out of the loop. No, in the loop. No, that was right. I had to do them both. So he only moves it once. That's the problem. set swapping to true. Inside the if statement. And the end at that part. Huh. Decorate M by 1, return the sorted list. Everything's nested in the right way. I'm just trying to think what's happening. So step it through. So while swapping is true, so swapping is true at the beginning, then we set it to false. So for I in range 1 to end, so it starts at 1, and then it's going to be I minus 1, so it's going to be nums I minus 1. So at the beginning it's going to be 0, so in this scenario it's going to be 5. So 5 and 7. 5 is greater than 7. Wrong, so swapping is still false. So it goes back. It does n minus 1 and goes back around again. This time around it's 2. So then it's going to be 7 and 3. So then if 7 is greater than 3, which it is, then swap them. So then put 7 in the 3 position and 7 in 3 position and 3. Sorry. I got that wrong way around. So I minus 1 is greater than that. Right, so yeah, so then I minus 1 is 3. That's right, yeah, because it swaps it. And then that and then the regular number I is 7, that's set swapping to true. Then it comes back round, it's still true, so then it goes down again. But I guess it never goes back to what's end for? Decrement n by 1. So let's start from 2. So at that point, we'll have swapped 0, 1, and 2. So that would be 7 at that point. It never goes back and compares the first one. For I from the second element to the end. But you never sort the first thing then. Might need a little bit of help with this one. Not gonna lie. Right. That's a pseudocode. Why have I messed up? What if I just comment that out? Like, I'm not sure about that part. Okay, infinite loop, fair enough. What if we're only decrementing if there's a match? Doesn't really make a difference because it seems to be dependent on. Let me just print out these. So like print, and it's going to be I minus 1 to I. So it goes 5, 7. In fact, we'll do so 5, 7, 7, 3 hit. And it moves them, then it does 3, 6, 6, 8, 5, 7, 7, 3 hit. Then it does 3, 6, 3, 6, 5, 7, 7, 3 hit, 5, 7. Hmm. Hold on. Right. Okay. Don't know what's happening there. Okay. We did it. We did it. Woo! W for me. Yeah, I got a little bit confused. I think it's because of what I originally had was I just had nums going straight into this, and that didn't seem to work. But when I copied it first, it then worked better. I'm not really sure why on that one, to be honest. But yeah, okay, we had the logic right. It is what it is. With just something like the way it is with Python. I'm still getting used to. Yeah, so they did exactly that. So they did the same thing. So temp. Okay, yeah, so like the swap over, right? Yeah, I just did it slightly different way. That's basically the same. So bubble sort, big O, best and worst case. Sometimes it's useful to know how the algorithm will perform based on what the input data is instead of just how much data there is. In the case of a bubble sort and many other algorithms, the best and worst case scenarios can actually change the time complexity. Best case, if the data is pre-sorted, bubble sort becomes really fast. Can you see why? Worst case, if the data is in reverse order, bubble sort becomes really slow, but still in the same complexity class as random data. Can you see why? Yes, because if it's already sorted, well then, like every time it only needs to loop through once, basically. If everything is wrong, it needs to loop through everything in order of magnitude to be able to get it. So what is bubbles sorts big O complexity? It's it's nested things, so I feel like it's going to be this is trying to remember now. O to the power n to the power of 2. I feel like it's that. It's not constant time. It's not log I've forgotten this one, exponential, and like it's not logarithmic. This one. Ugh. Oh, I got it right. Gosh, all right, let's explain why I'm right. So an excellent question. Understanding why bubble sort has a big O complexity of O(n) to the power 2 is key to grasping its performance characteristics. Let's break it down. So O(n) to the power 2 means that the time the algorithm takes to complete grows quadratically with the size of the input of n. If you double the input size, the time taken will quadruple. In the case of bubble sort, O to the power of n, complexity comes from the nested loops you see in the implementation. Yeah, that's where my thought was coming from, was like 2 nested loops looks like, doubling up stuff. So, outer loop, while swapping in the worst case scenario, when the array is sorted in reverse order, this loop will run approximately n times. Each pass moves the largest unsorted element to its correct position at the end of the array. In a loop, inside each iteration of the outer loop, this for loop iterates through the unsorted portion of the array. In the first pass, it goes through n-1 elements, in the second n-2, and so on. While on average, this loop also runs roughly n times. Because you have a loop, for loop, running roughly n times inside another loop, the while loop, that also runs roughly n times. The total number of operations scales with n times n, which implies to n to the power 2. Best case scenario, yeah. Okay, yep, thanks for the explanation, Boots, makes sense. Okay, same again. So what are its best and worst case run times? So at best, n, and at worst that, because if everything is already sorted, it doesn't actually need to do anything, it just needs to run through once. So why bubble sort? Bubble sort is famous for how easy it is to write and understand. However, it's one of the slowest sorting algorithms, and as a result, it's almost never used in practice. That said, we covered it because it's useful thought exercise so that you can appreciate why more complex and perform algorithms are better. Let's cover those next. Whereas a good reason to use bubble sort: I need to save some memory, I need a fast algorithm that stays fast on large datasets, I don't have much disk space because I'm studying algorithms. It's definitely the last one. Merge sort. Okay, so already got through a few lessons so far, which is good. So merge sort, that'll be interesting. Insertion sort, quick sort, fixing, and then, yeah, cool. Okay. So merge sort is a recursive sorting algorithm, and it's quite a bit faster than bubble sort. It's a divide and conquer algorithm. Divide the large problem into small problems and recursively solve the smaller problems. Conquer, combine the results of the smaller problems to solve the large problem. In the merge sort, we divide the array into 2 equal halves, divide. Recursively sort the 2 halves. Merge the 2 halves to form a sorted array, a conquer.
First, let me explain the pros and cons of merge sort, and then we'll break down the algorithm step by step. Merge sort is much more efficient than bubble sort, which, if you're here slogging through an algorithms course, you probably already know a little bit about. In big O terms, merge sort is order n log n, which makes it a lot faster than bubble sort's shameful order n squared. Now, order n log n is about as good as we can do when it comes to sorting unsorted lists. But there are a lot of things that affect performance on a smaller scale that are worth thinking about. For example, merge sort's space complexity is less than ideal. It requires copies of the original list to work with, which means it's going to take up more memory than an algorithm that can sort the list in place. It's also slower than some other algorithms like insertion sort when it comes to sorting smaller lists. And that's because of the memory allocation, the copying, and even the overhead of the recursive function calls. All those things have a constant toll on the performance of the algorithm. So they don't really affect the big O, which is order n log n, but they do affect the performance in practice. And that effect is disproportionately bad on smaller lists. Okay, so how does merge sort work? Well, first we start with an unsorted list of numbers. We split the list into 2 parts, and we keep doing that recursively until each list has at most 1 item. Next, we start merging each of those lists back together. The process is actually pretty simple. We take 2 small lists, iterate over each item in both lists at the same time from left to right, and we just compare them, moving the smaller of the 2 into a newly sorted list. By the time we've moved all the way back up the tree, we'll have a fully sorted single list. It's a recursive divide and conquer algorithm. It uses a pair of recursive calls at each level to split the list into parts, all the way down until we have a single element in each list. Then it merges them all back up the call stack again by looking at each element in both of the lists one at a time. It's an n log n algorithm because it needs to be called recursively log n times. And at each level in the recursive call, all items in the list are compared.
Okay. So algorithm. The algorithm consists of two separate functions, merge sort and merge. Merge sort divides the input array into two halves, calls itself on each half, and then merges the two sorted halves back together in order. The merge function merges two already sorted lists back into a single sorted list. At the lowest level of recursion, the two sorted lists will each only have one element. Those single element lists will be merged into a sorted list of length 2, and we can build from there. In other words, all the real sorting happens in the merge function. Okay. So merge sort pseudocode. So input A. So an unsorted list of integers. Okay. If A, the length is less than 2, we've already sorted, so then return it. So if length of nums is equal to 2, or I should say it's like, less than or equal to 2, then return nums. Split the input array into two halves down the middle. Okay, so I forgot the first equals, I think it's like, is it nums dot slice like that, or is it slice? Forgotten how it works. One sec. Slicing lists in Python. Examples, omitting sections, numbers, negative indices. All right, okay, so just do it like so. Whoops, wrong part. So it's going to be nums. It's going to be 0 to say like halfway equals length of nums divided by 2, and then is there like a function for sort of like ceiling or like rounding up or down? So like ceiling, I can't remember. Let's do that for now and see what it does. So from there to halfway, and second is going to be nums, and then halfway, then length of nums. Okay. I suppose you don't even need to do that, do we? It's just halfway to end, not to halfway. Okay. Call merge sort. Call merge sort twice. Once on each half. So that's going to be merge. Whoops, am I in the wrong thing? Oh no. Score merge sort. And it's going to be twice, once for each half. So first, and then merge. Whoops, merge sort. Second. Return the result of the calling merge sorted right side on the results of merge. Return the results of calling merge. All right, okay, so you're right. Sorted left side, sorted right side, and it's going to be on the results. Okay, so return sorted left side, sorted right side. Okay, so then the merge pseudocode. So the merge pseudocode is create a final list of integers. So final that set I and j to be equal to 0. They'll be used to keep track of indexes in the list of A and B. So I and j, can you do it like that? So 0. Use a loop to compare the current elements of A and B. Yeah, A and B being, sorry, this. Use a loop A and B. If an element in A is less than or equal to its respective element in B, add it to the final list and increment I. Otherwise, right, hold on. So for A in first, is less than or equal to respective element B, add it to the initial final list and increment I. Otherwise, add item to B. So like if A is what? Is less than or equal to second. B in second. Typing's all over the place today. So then if A is less than or equal to B, then we do what? Then add to the final list, so final dot append I, and then increment, so then I plus equals 1, else then final dot append B, and then increment j, so j plus equals 1. After comparing all the items, there may be some items left over, either in A or B. Add those extra items to the final list. Return the final list. Hold on, let me see. Ceiling, slicing lists. One point five. Floor division, there we go. Hold on. Ah, right, okay. I'll look at that in a minute. Oh, thank goodness. Kept my code. It's right in there for a minute. So it failed. Multiple lists. Basically, just trying to figure out how to like handle multiple lists concurrently. So like, user for to compare. We don't know which one's the bigger one. So let's do print first, second. So look at this. Ceiling, floor. Oh, hold on, I got something wrong here. So merge sort code. Call merge sort twice on each half. So split into two. And then it says call merge sort twice, once on each half. Oh no, that's right. That's right. And the results of merge sort calls. Return the result of. Oh, dummy me. Hold on. Declare variables. Multivariable declaration. Whoops. Oh, I have to put 2 values for each, right? Okay. Okay, so expecting 1, 2, 3. Test completed. So we got actual 2. Yeah, so this is what it was saying. It was like there'd be some leftover. What did it say to do? After preparing items, there may be some items left over in either A or B. Add those extra items to the final list. Okay, so then how do we do that? So final dot append. Can we just do A and B like that? Whoops, that's a bit. Left my streak. Final dot append B. Final. Python compare to lists. Compare two lists with different length. Use a zip function to pair up the lists, counting all the differences, then add the difference length zip. Only iterate over the items that can be paired up, but there is little point iterating over the remainder. You know those are all to be counted as different. Hmm. I just wondered if there was a smart way of doing it, basically. Hmm. So first A, and I guess B is going to be B is equal to second. How do you get index of it like an item? So index. Python get index of item and list. Oh. Index. So it's going to be first. Wait, how'd it go again? Index of A. In A and B. Leftovers. Hmm. Let's check. Does this decrease stuff that's left over A and B? Set I and j equal to 0. They'll be used to keep track of indexes in the input lists A and B. Use the loop to compare the current elements of A and B. If element A is less than or equal to its prospective element in B. Inputs A and B. B add it to the final list, incremented by I. Otherwise, okay, right. I think I got it now. So, So set I and j. Hey peeps, how's it going? So set I and j equal to 0, they'll be used to keep track of the indexes in the input lists A and B. So A, that's going to be A, that's going to be B, right? Use a loop to compare the current elements of A and B if element in A is less than or equal to its respective element in B. Add it to the final list and increment I. Otherwise, add the I and B to the final list and increment J. After comparing all the items, there may be some items left over in A or B. Add those extra items to the final list. So I guess let's just print and just see I and J by the end of it. Final, see what it is. 2 and 1. So we do final dot append, and then we do first. We do slice from I to end, and then we also do append second J until end, right? Something like that. No. How do we merge? So merge. We'll get a lot of love hearts from people, thanks. Merge lists. List concatenation. Or you just plus it. Okay. Well, that didn't work in the slightest. Set ij to equal 0, they will be used to keep track of indexes in the input lists A and B. Use a loop to compare the current elements of A and B if an element in A is less than. Love from India, thanks guys. Sending love back. I'll do the heart sign, peace. Use a loop to compare current elements of A and B. If element in A is less than or equal to its respective element in B, add it to the final list and increment I. Otherwise, add the item in B to the final list and increment J. Continue until all items from one of the lists have been added. Okay, so we don't need to do a nested one, right? So take that out. So then B equals second dot J, right? It's less than or equal to. Otherwise, continues all items from one of the lists have been added. I have to use a while loop. Continue until all items from one of the lists have been added. So emptied. So we have a thing saying emptied. Emptied one list. Oops. One list equals false. And I guess it's say for while emptied one list is equal to false, and keep doing this. Can we get an increment when we're doing a while loop? While guess we can have a counter. First, second. I need to slice these things out only. So like slicing lists. List slicing goes to extract portion. The syntax for slicing. Such optional items. Is it also edit the original? Python. I guess remove item from list. Remove specified index. Pop. So I guess we could pop it, can't we? So pop I, and then pop G. First and second. So then if we get to a point where so I guess if length of first is equal to 0 or length of second is equal to 0, then emptied one list equals true. Dang it. So print step. Oh, feels like it's like such a noob. I J emptied one list. Let's see. So step 0 1 true, emptied one list. Final first second. Uh, lists. Oh, final equals. Whoops a daisy. So if So it's going to be end conditional this. So if end conditional then I guess return. So first plus second. Oh yeah, now I remember now. Right, okay, if end conditional that. So print first, second. Oh my goodness. Having a real mare of this one. How long have I been on this now? Too long by the looks of it. Baptism of fire, come on. Right, so we've done that. This seems pretty solid. It's just this part. So it doesn't really explain what you want to use I and J for. It'll be used to keep track of indexes in the input lists A and B. Use a loop to compare the current elements of A and B. If the element in A is less than or equal to its respective element in B, add it to the final list and increment I. Otherwise, add the item in B to the final list in increment J. See, all items from one of the lists has been added. And then the leftovers. But the problem is it's popping on something. And this only goes through one step. So appends B, file stage. Suppose we do that first. The way to stop a while loop, so while break it. Use the break statement. Is the one. Break, I suppose. Is not going as expected at all. I'm going to have to call him Boots for this one. I'm not getting it. Boots, I'm going to have to call in a favour. I'm willing to pay for answers. Yeah. Come on, Boots, help me. I'm struggling. Okay, let's use a bit of sorcery and critical thinking in your wedge function. Using pop I and pop j to remove elements by index from both lists every loop. What happens to the indices I and j as the lists shrink? Could be why you see an index out of range. Yeah, it could be. When merging, you need to modify the original. When merging, do you need to modify the original list with pop, or could you simply read the values at current positions and use indices to track your progress? After one list is empty, how can you simply add the rest of the other list to your final list without popping more elements? Can you think of a way to iterate over both first and second using only I and j indices appending values to final without removing elements from the list? Try reworking a loop. Don't touch the lists themselves. Just read the elements. What would that look like? I did do that to start with, but it didn't really make sense. So it says, when merging, you need to modify the original list for pop. After one list is empty, you can simply add the rest of the other list to your final list without popping more elements. It'd be like I to the end and then oops, J to the end, something like that. Yeah, I'll do this. So four, A in first. Don't need none of this. What am I using I and J for? I've adapted it, but still having issues. In your merge function, you made some changes, and that's the spirit. Let's ponder. In your merge function, you're iterating over elements at first, but selecting what if the second is shorter than the first, or vice versa. What happens to the indices? Then ideally, merging should continue as long as there are items left in both lists. Usually, this is done with by. Yeah, that's what I kind of did first time around, right? I did a while loop. So while I is less than length of. All right, okay. See where it's going now. So first. And J is less than length of. Right, now it makes sense. That wasn't super clear, that. Okay. But maybe it's me being dumb, to be honest. So then A is equal to first I, J. Ideally, image blah, blah, blah. You should continue to use a for loop over first. Should you be using a for loop over first, or should you be comparing first and second I while using while loop and controlling I and J yourself? You might what might happen if you just loop over one and not the other? How could you rewrite the merging logic? Blah blah blah. Try pinning out the loop structure. How can you loop until one of the lists is exhausted? Always comparing the current item of first and second. Using a while loop now. How does it look? Excellent progress. Your merge function logic is now much closer to the correct merge pattern. But there's a key enchantment missing in your merge. Oh, merge sort function. Alright, okay. You currently return nums as is if length is less than 2, which means that your 2-element list, you don't sort them, you simply pass them back. Merge or expects all this. But didn't it say if the length of A is less than 2? Oh, less than 2. Oh my god, no way, really? Is that it? Which means that for 2 elements you want to sort them, you simply pass them back, merge or expects all rays. Oh, dummy. There we go, we got there in the end. Blimey, what a palaver. Right, okay. And we have to start remembering, so this is going to be key, I think, to a lot of the other sorting algorithms, is when you're looping through and sort of handling indices with like 2 sort of common lists, is you can't have like 2 indices, sort of indexes in a for loop, so you kind of have to arbitrarily kind of like create them and then, append them kind of inorganically, but whatever. Hey Nicholas, you're right. Nobody there on Twitch at the minute. A few people on YouTube. So YouTube peeps. Oh gosh, we finally got through that. It was a slog. But trial by fire. So what is merge sort's big O complexity? Well, my logic is a little bit different, so. Oh, right, okay, I see. I kind of took a different approach of just like plobbing them together. This one. What is merge sort's big O complexity? I'm not sure. I can't really think. There's no nested loops. Well, I suppose there is, with its recursive nature. I'm not really sure, to be honest. It's not constant time. There's loops. And I guess by the length, I think it's this one. Yes. Now my thing for it is that I can't remember the logarithmic part stuff, but basically like, yeah, let's have Boots explain it because I'm just going to be chatting. Certainly, let's go over why on times log n is the correct big O complexity for merge sort. Merge sort works by dividing, repeatedly splitting the list into 2 halves until you have lists of size 1, merging, combining the small list back together in sorted order. Let's break down the steps. Each time you split, you cut the list in half, just like a binary tree splitting. The number of splits needed to break a list of n items all the way down to a single element elements is log squared n. At each level of merging, every element in the array is considered a merge. This means at every level of the split, from a single elements back up to the full array, you process all n elements, put it together. There are log n levels of splitting / merging. At each level you do on work. Multiply those. Right, okay, yeah. On times O log n. Why not another answer? O(n) to the power of 2 is typically for source sorts like bubble search. Is only first for simple operation, best case scenarios in some case algorithms, not for merge sort. O log n would be only tree depth was involved, not the whole array each time. If you want to also walk you through steps with a concrete example list. Yes, walk me through, please. This is so extremely helpful. Appreciate your help, mate. Thanks, Saul. Appreciate people watching. Hope you're getting some value out of this. Boot.dev is extremely valuable. If you can afford to get it, I'd say so far. Right, so he's explaining. So let's walk through the merge sort on a small example list. 4, 1, 7, 3. So divide the list. First, split the list repeatedly in half until you get single elements. How many times do we split? 2 splits from 2 to 2 to 1. So log squared 4 equals 2. Okay, why do we jump to log squared? That's what I want to figure out. I want to understand, why do we jump to log squared? Merge back together, sorting as we go. Now each pair is merging. So how does this show on times log n? For n equal to 4, we need log. Merge it. Why do we jump to log 2? So that's a sharp question. Let's dig into why the logarithm base is 2 in n times log n. First, let's talk about log squared n in this context. It's because every division step splits the list in half. The base of the logarithm matches how we're dividing half, half, half. If you keep halving a list n times, the number of times you can do this before you're down to single elements is log 2. Okay, so 2 splits. 2 levels of splits, okay. Oh, because it's the halving, right? The base of the logarithm matches how we're dividing. So that's 3 splits. So for 8, so how many times do we need to split 8 in half before we get to 3, basically? So 1, 2, 3 times, we need 3 splits. Big O, why does the base not matter? In big O notation, we just write log n. Either it's technically base 2, in which case, why do we immediately assume it's log? An excellent question. We don't assume it's a logarithm. There's a reason behind it, grounded in how we divide and conquer approach works. Let's break it down. Whenever an algorithm repeatedly splits a problem in half or into any fixed number of pieces, the number of splits it takes to reach the base case grows like a logarithm. Specifically, you can split an array n elements in half about log 2n times before you end up with a list of size of 1. Why log n? Imagine you have n things and you keep halving them. So after the first split, n divided by 2, second split, n divided by 4, third split, n divided by 8, keep going. You stop splitting when you reach a group size of 1. The number of times you can do this is the answer to n divided by 2 to the power of k equals 1. So n is 2 to the power of k. K is, that's not an assumption, it's a result of math behind repetitive halving. So just ask, what is a log? How do you spell logarithm? Logarithm with an N? No. What is a logarithm? A fine question. In computer science, understanding logarithms is extremely helpful because for analyzing algorithms, a logarithm answers the question, to what exponent must we raise a base number to get another number? In symbols, the logarithm base 2 of 8 is written as log 2 8. It asks 2 raised to the power of 2 raised to the power to what power gives us 8? Answer is 3 because 2 to the power of 3 is 8. In programming and algorithm analysis, we often use base 2 logarithms because computers operate with binary splitting. If you have a list repeatedly, the number of times you can do it is log 2. Okay. Would you like to try how do you spot when a logarithm is taking place? I just want to really understand this when I get a firm grasp on it. So a very practical question. In programming algorithms, you usually know a logarithm is involved when the problem or algorithm has one of these features: repeated halving or doubling. Whenever you repeatedly cut something in half or double it, you're in a logarithm territory. Examples: binary search, divide and conquer algorithms, tree structures. Binary trees often have log relationships. Depth or height of a balanced tree with n nodes is log 2n. Operations like searching, insertion, or deletion in a balanced BST take log time. While loops with divide by 2 steps. If you see a loop where the update is x equals x divided by 2, probably runs log n 6 times before stopping. Exponential growth or shrinkage. The problem size grows or shrinks exponentially. The number of steps to reach a limit is logarithmic. In general, look for places where the size of the day is rapidly shrinking or growing, particularly by factors like 2. Would you like to try and spot log process in a snippet or see example problem? Help me spot a log process. Okay, absolutely. Let's practice spotting a logarithmic process. I'll give you a few code snippets, see if you can identify which ones include a processor running to a logarithmic time. Focus on how a variable changes at each loop. Which of these snippets do you think B? Because the because x is halving each time. Exactly right. You spotted the logarithmic process basically. Snippet B halves x each time through the loop. Each iteration is divided by 2, so the number of times this loop runs is determined by how many times you can have n before getting to 1. That's exactly what logarithmic describes. Is logarithmic the same or similar to exponential? Great question. Well, logarithmic and exponential processes are related, but they are almost opposites. Exponential means the value grows or shrinks by multiplying each time. Common example, doubling, halving over and over. A typical exponential function is 2 to the power of n. Grows very quickly. Logarithmic means describes how many times you have to multiply or divide to reach a value. It measures the number of steps, not the value itself. Okay. Example, how many times can you cut n in half before reaching 1? Relationship. If y equals 2 to the power of x is exponential growth, then x equals log 2 y is the opposite operation. Logarithms are the inverse of exponentials. Okay. Exponential. Analogy. Exponential. I double my gold every day. How much will I have after 10 days? Logarithmic. How many days will it take to reach 1,000 gold if I double? Yeah, that's beautiful. This tool with Boots is absolutely like phenomenal, like explaining things and stuff. It is so good. Absolutely incredible. Like so good. Lane, if you're out there watching, mate, be proud. Is very, very much incredible. So why merge sort? So with the end of merge sort, even like though kind of mush my brain. We've got a couple of things. Then we've got insertion sort. We'll see how far we get. We might get to quick sort. I don't think we'll get and do quick sort, but we might be able to get through insertion sort if I don't have a big brain fart again. Pros, fast. Merge sort is much faster than bubble sort. O(n) log n instead of O(n) to the power of 2. Stable. Merge sort is a stable sort, which means that the values with duplicate keys in the original list will be in the same order in the sorted list. Okay, cons. Memory usage. Most sorting algorithms can be performed using a single copy of the original array. Merge sort requires extra subarrays in memory. Recursive. Merge sort requires many recursive function calls, and in many languages like Python, this can incur a performance penalty. So there's a reference to it. Where might merge sort be a good idea? Need a simple sorting algorithm for a small data set, it can be very quickly. Need a fast sorting algorithm, and memory isn't an issue. The next question, which function is recursive? Merge sort is. It calls upon itself. Okay, insertions sort. We're going to be writing another one. So let's see. Okay, insertion sort builds a sorted list one item at a time. Insertion sort builds a sorted list one item at a time. It's much less efficient on large lists than merge sort because it's O(n) to the power of 2, but it's actually faster, not in big O terms, but due to small constants that merge then merge on sort on small lists. So explain a video. Let's listen to it.
First, let's talk about when and why you actually use insertion sort, and then I'll break down the algorithm step by step. Insertion sort is interesting because it's actually really slow in the average case, order and square, but it has a niche use case where it's actually used in the real world because of how fast it is. And that's when the data is already mostly sorted and when the data set is very small. Some sorting libraries will actually use insertion sort when the data set is small enough and fall back to a different algorithm on larger sets. So how does it work? Well, it's actually one of the simpler algorithms. We start with an unsorted list of numbers. We'll iterate over each index or each position from left to right. We're going to keep track of two indexes, I and j. I will be the index of the current number that we are on, and j will start at that same position, but it'll actually move to the left. I'll show you in a second. Now, because it's a look-back algorithm, we can actually skip the first index. We'll set I and j equal to position 1, or index 1, which is etc. Now, the number doing the swapping will be the number at j, and the number at 1 less than j. I actually has nothing to do with the swapping. It's just kind of keeping our place in the algorithm. So we look at the number at position j, at the number at position j minus 1. And if they're out of order, we're going to swap them and decrement j. If they're already in order, then we can just move on and increment I. And whenever we increment I, we also move j back up to where I is. It seems really fast at first because I and J are close to the start of the list, so the amount of backtracking J has to do isn't very much. But you'll notice as I and J get larger and larger, we're going to have to look back through more and more of the list. Now here's what a sped up version looks like on mostly sorted data. Here's what it would look like on completely random data. And here you can watch it be really slow on reverse sorted data.
Great explaining video. So, assignment. Our influencers want to sort their affiliate deals by revenue. None of our users have more than a couple hundred affiliate deals, so we don't need an n times log n algorithm like merge sort. In fact, insertion sort could be faster than merge sort, and it uses less of our server's memory. Complete the insertion sort function according to the given pseudocode. So for each index in the input list, set a j variable to the current index. So for each index in the input list, so whoops. So j equals set variable j to the current index. So I don't even need that. So for j in a range, and it's going to be 0 to length of nums. Its current index, while j is greater than 0, actually, hold on. J equals 0, start like that. So then, while j is greater than 0 and the element index is great. While j is greater than 0, so while j is greater than 0, and the element in the index j minus 1 is greater than the element index j, and while nums start at 1. So while nums j minus 1 is what, greater than the element index j, so that in j. Swap the elements indices j and j minus 1, decrement j by 1. Okay, swap the elements. So nums so temp equals nums j. So then we're going to say nums j equals nums j minus 1. Then we're going to say nums j minus 1 is equal to temp, and then decrement j by 1. So j minus equals, whoops, minus equals 1. Return nums. Wop, wop, wop. J equals. So for each input, so we're going to do for num in nums, J equals current index. It's going to be nums.index num, and then paste this. So while J blah 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 blah. Is this right? Yes. Okay, I did it. Surprised I got through that fast. There we go. So they kind of capsulate what I did in some like fewer lines. So for I in range length of nums, so I go from like 0 to whatever the length is, J equals I. While J, the same thing I did there. And then, oh, that's interesting. You do that in one line. Okay. So insertion sort for has a big O notation of on to the power 2, because that is the worst case complexity. The outer loop of insertion always executes n times, while the inner loop depends on the input. Yeah. Best case of the day is pre-solid insertion sort becomes really fast. Can you see why? Average case, the average case of O n squared, because the inner loop will execute about half of the time. Worst case, if the day is reverse order, it's still on to the power 2, and the inner loop will execute every time. Yeah. Which insertion, what is the insertion of big O's complexity? You just told us what it was. And then what is the insertion of big O's complexity on an already assorted array? An already assorted array, it's going to be I think it's going to be on. No, it's got to be something, hasn't it? N log n. No, log n. N. Crap. I should have gone with my gut, because it basically it's constant time, right? Because it only needs to go through things once. That's how Boots explain it. See if that's why. So excellent question, young apprentice. Understanding why insertion has different complexities based on the input is key to mastering Big O. Let's look at the insertion sort function provided. Outer loop, inner loop. When the array is already sorted, the for loop, or the outer for, will still iterate n times. Oh, sorry, it's not constant, it's just linear. Right, yeah. The for loop, outer loop will still iterate n times, where n is the number of elements in the array, because range len nums will always go through each index from 0 to the length. Now consider the inner while loop. So while blah 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 blah, if the array of nums is already sorted, then for any j greater than 0, the conditions will never be true. Why? Because in a sorted array, the element j minus 1 will always be less than or equal to, yep. So for each, this means the body of the while loop will not execute for any iteration out of the outer loop. So for each of the n iterations of the outer loop, the inner while loop effectively performs a constant number of operations. Yeah, okay, yeah. That's basically what I expected. Why use insertion sort? Fast for very small data sets, even faster than merge sort and quick sort. We'll cover that later. Adaptive. Faster for partially sorted data sets. Stable. Does not change the relative order of elements with equal keys in place. Only requires a constant amount of memory. Inline can sort a list as it receives it. Why is insertion sort fast for small list? Many production sorting implementations use insertion sort for very small inputs under a certain threshold, very small like 10ish, and switch to something like quick sort for large inputs. They use insertion sort because there is no recursion overhead, it has tiny memory footprint, it's a stable sort of described as above. Is insertion sort useful in production systems? Yes, but only very small inputs. And same thing again. So which algorithm uses the least memory and which is generally faster, respectively? Insertion sort and which is generally faster, respectively. Insertion sort and merge sort. Okay. Quick sort. This might be the last thing for tonight. In fact, it will be. Yay, we get to watch another Lane video. Huzzah! So quick sort is an efficient sorting algorithm that's widely used in production sorting implementations like merge sort. Quick sort is a recursive divide and conquer algorithm. Divide, select a pivot element that will preferably end up close to the center of the sorted pack. Move everything onto the greater than or less than side of the pivot. The pivot is now in its final position. Recursively repeat the operation on both sides of the pivot, conquer. The array is sorted after all elements have been through the pivot operation. So, explain a video. Let's watch, Lane. Show us what you got.
Quicksort is fast and efficient, and unlike some of the other algorithms that we've covered on this channel, it's actually used in the real world. Looking at you both. Quicksort is a divide and conquer algorithm, just like merge sort. And while it technically has the same big O complexity as merge sort, order n log n, it doesn't require so much memory, and it doesn't have to copy elements from sublist to sublist. It actually sorts the entire list in place, which means that it can be more performant. Alright, let's dive into how it works. We'll start with a random list of numbers. The first thing we need for quicksort is a pivot number, and to keep things simple, we'll just arbitrarily use the element at the end of the list. In this case, 5. We need 2 pointers, I and j.
Hold on. Let me listen to this again.
Unlike some of the Quicksort is fast and efficient, and unlike some of the other algorithms that we've covered on this channel, it's actually used in the real world. Looking at you, Bubblesort. Quicksort is a divide and conquer algorithm, just like merge sort. And while it technically has the same big O complexity as merge sort, order n log n, it doesn't require so much memory, and it doesn't have to copy elements from sublist to sublist. It actually sorts the entire list in place, which means that it can be more performant. Alright, let's dive into how it works. We'll start with a random list of numbers. The first thing we need for quicksort is a pivot number, and to keep things simple, we'll just arbitrarily use the element at the end of the list. In this case, 5. Next, we need 2 pointers, I and j, to keep track of things, as we're going to be swapping them around. I will start at index -1, which of course isn't a real index, but we need to be able to increment into index 0 on the first swap. Then j will start at index 0, which is 8. So in this case, we'll be comparing 8 and 5. And because 8 is not less than 5, meaning j is not less than the pivot, we don't move I, but we do increment j. Now we do it again. We compare j to the pivot, 3 to 5. And because this time j is less than the pivot, we increment I, then we swap I and j. Now I understand that it's a bit funky. We're comparing j and the pivot, but actually swapping I and j. Just remember that. All right, and now we just do it again. So now we'll compare j to the pivot again. In this case, 2 and 5. And again, because j is less than the pivot, we increment I, and then we swap I and j. Next, we compare 9 and 5. Now this time, j is greater than the pivot. So no swaps. We move j forward, but we do not move I forward. 1 is less than 5, so we move I up, and we swap I and j. 7 is greater than 5, so no swaps here. 6 is also greater than 5, again, no swaps. 10 is greater than 5, no swapping. 4 is less than 5, one last swap. All of the numbers at or to the left of I are smaller than the pivot, and all of the numbers to the right of I are greater than the pivot. If we swap I plus 1 with the pivot now, then the pivot will be in its perfectly sorted place. Now, that's just one round of the partition function in quicksort, but frankly, it's the interesting part. The way we turn this partition function into a full-blown quicksort is by recursively calling this partition function. So we'll continuously partition, do this algorithm, over and over on each half of the list until the full list is sorted. Now, remember how I mentioned that quicksort is generally more performant than merge sort? That's true, but it does have a dark side. If we consistently pick the smallest or largest element from the list as the pivot, it gets really slow and will actually degenerate into order n squared in big O terms, which effectively makes it a bubble sort equivalent, which is something that no sorting algorithm wants to be. But honestly, that shouldn't scare you. There's pretty trivial ways to make sure that quicksort never degrades. For example, we can just check and make sure that the list isn't pre-sorted. We could randomize the list before sorting it, or we could even pick the pivot at random for maximum chaos. Anyways, optimized versions of quicksort are used all over the place in the real world. Most languages' standard libraries actually do use quicksort, at least for part of the standard implementation of their sorting algorithms. Now, so you can properly visualize it end to end, here's a full animation of quicksort on a larger data set. And here's another full animation, but where the list is already sorted and the performance